slowly start. Hello everyone, in this pretty niche topic like Mobius. The title is Mobius, writing your own .NET runtime running on .NET Core, or maybe .NET 5 as it is called today. So this is a pretty niche thing. I really hope you will enjoy it, and I will enjoy the recording if you are watching the recording now. So my name is Konrad Kokosa. Just a few words about me. I'm a .NET related guy, which is freelancer, trainer, consultant, speaker, doing many things related to advanced .NET stuff, like investigating various diagnostic problems in .NET world. Also really liking the topic of .NET internals, how the .NET is really working underneath. So we are providing also as a .NETOS initiative premium .NET content about stuff, which is, let's say, advanced in the .NET ecosystem. And for example, if you like .NET internals and you would like to know how those are working, I recently started this .NET GC internals mini series on YouTube for free, totally once a week. Every Wednesday, I'm just describing you how the .NET GC is implementing. Phase by phase, I will be describing this in detail. So if you like that, just Google for .NET GC internals. Probably you will find it on YouTube. So that's about me. And regarding the topic, one question, the very first question for you is, for example, have you ever wondered how .NET runtime really works underneath? Maybe you did, maybe you was wondering, but it was pretty hard to find a good motivation to do something with that, maybe to read about it, because it is not super practical thing. So maybe you have wondered, but not necessarily you have read anything about that. Another question, maybe even more advanced, is whether you ever dreamed of contributing to .NET runtime. And this is even more sophisticated question, like, okay, probably maybe you have dreamed about it, but you was really afraid of doing so because it is so huge, complex code, C++ code. So why I would ever imagine contributing to such huge and popular thing like .NET runtime? So I will answer those questions at the end. And why the whole idea of the Mobius, and the Mobius is, as the title says, the runtime which is running on the another runtime. So before answering why I need, maybe not need, but why I have imagined something like that, let's just have a few words about the .NET itself. So I wouldn't like to overwhelm you with the super sophisticated low-level stuff during this talk, because probably it would be too boring, but mostly describe some high-level concepts about this Mobius idea thing. And to have the .NET runtime implementation, first of all, we need an answer to a question what the .NET is in the end. And from formal perspective, it is just a specification. A .NET, we can say, is an open specification, a technical standard developed by Microsoft, obviously, that is standardized in ISO, ECMA documents, saying what it is in the end, describing executable code and the runtime environment and all the stuff that it needs to be implemented to say that you have an implementation of .NET. And this specification name is Common Language Infrastructure, so you can meet this name also pretty often. And it is specified in this ECMA 335 document. So if you would like to investigate a little bit what this .NET thing is defined, you can investigate this document. Do not mislead it with another one, ECMA 334, which is only about C#. And this is not the story that we will cover today. We are covering the whole runtime ecosystem part, which is Common Language Infrastructure. And if you'd like to take a look, there is also a great article from Matt Warren that is just kind of overview what's inside this ECMA document. Okay, so we have this ECMA 335 document describing our common language infrastructure. And then it contains mostly of 4 elements, building blocks, the common type system that will describe what set of data types we are available. So there will be in description that we have integers, doubles, and other types that should be exposed by this .NET ecosystem. Then there we have the metadata, which is information about the program structure and data, as you probably know, and the description how this metadata should be described and stored. The common language specification, something a little bit less popular, which is a kind of subset of rules that should be met to say that your language is CLS compliant. It is a set of, I said subset because we are used to more superset, let's say, because for example, C# is not by default CLS compliant. There are some possibilities that makes the default C# compilation not CLS compliant. That was from the times that Microsoft was designing all these things for having multiple various languages, but now we have C#, F#, and we should not really care about CLS compliancy so much. But this is also not the topic for today, because we have the last building block here, the virtual execution system, and this is the fancy name for the runtime. So virtual execution system loads and executes a program that is CLI compliant. CLI, it meets all these things required and specified in ECMA standard. So we need something like that. And in the end, this virtual execution system, which we can also simply say runtime, is just a piece of code executing this CAL code, common intermediate language, which is also defined in ECMA, which is kind of bytecode, simply saying what your application is doing. Obviously, it needs to do that knowing all the other stuff, so it is aware of common type system, of metadata, and we may ignore the compliance of the language subsystem because it's not necessary. So we have this virtual execution system, we have the standard, and we have various implementations of it currently, pretty a lot, you can say. Obviously, we are aware of .NET Framework, .NET Core, .NET 5. This is a .NET based .NET-based conference, so we all are using those runtimes, which is awesome. And then we have also Mono, which is getting more and more popular, for example, mainly because it starts to run pretty important things like Blazor, WebAssembly, Xamarin, Unity Game Engine. They are all based on Mono. Then we have less popular ones like .NET Compact Framework, .NET Micro Framework for small devices. We have, even before the open sourcing .NET Core, we had the Rotor, which was shared source common language infrastructure and academical initiative to provide open sourced version of the runtime, mostly for just learning how it works. And there was also pretty awesome .NET Anywhere implementation of ECMA created by the one guy, Chris Bacon from the Google, that just made it, and it was able to produce something that was working to the extent it was working so good that the initial Blazor WebAssembly was based on this runtime, which is currently postponed and frozen, but it works. You can look at it. It is open sourced. And even more exotic ones like .NET GNU or Portable.NET, which was mostly for running multi-platform things on Linux. And it all happens that all this is obviously written in C, C++, in unmanaged languages, which is pretty understandable because obviously the runtime needs to run fast. It is unmanaged thing, it is unmanaged application that is not, it should run using the system calls, and it should be as close to the hardware as possible, probably, which is our intuition. However, the part of the runtime which is C++ based is not so obvious. Like, it is not that the whole runtime needs to be written in C++, and we are seeing it currently, for example, in .NET Core, .NET 5. We can see that more and more parts of it are being ported to C#, which may be pretty surprising. So it is not that the whole part of the runtime is currently written in C++. It has some benefits to take a code from the runtime written in C++ and port it to C#. One of the, let's say, soft skill based is that this has a better maintainability because it is just in C#, so more developers will be able to maintain it and, for example, to contribute to it. Moreover, it is out-of-the-box multi-platform. So if you have a code that is written in C++, there are big chances it is somehow per platform based. And then if you port it to C#, you have out-of-the-box multi-platform code that will be just JITed by the runtime. And there are also performance benefits. So if you have a code in C++ in the runtime and your application needs to call it, it needs to make this managed to unmanaged transition, which is just an overhead. It reduces the flexibility of the GC pauses, for example. So having no transition at all is just profitable also from the performance perspective. And that's why we will see that direction of porting some parts of it. There is an open issue to port the whole JIT and GC to C#, which is kind of dreaming of, and it will probably not happen in the full runtime. But some parts are indeed ported, like some helpers used by the JIT are indeed recently ported to C#, like the helper which is used for the unbox operation or when we store or read a reference between objects. So we see this, that even so low-level stuff like JIT is starting to use some C# code. Even there is the pretty huge project now to port the whole thread pool from the C++ code inside the runtime to make it multi-platform, better, well implemented in C#. Some sorting primitives were recently ported to C#, and we can read about it in this famous .NET performance improvements by Stephen Taub, that it just gives us real benefits in terms of performance, or comparing enums were ported. So yes, this is the direction we will see, probably. So this is not so obvious that everything should be in C++. Moreover, there are always some projects to make almost everything in C#. Like we have this core RT project, when the goal was to write as much part of it in C# as possible. The whole type system was written in C#, for example. That was another runtime implementation just to be kind of managed one. Obviously, maybe not obviously, but the goal was here to write it as much as possible, but still such low-level parts like GC or JIT were still written in C++. So it is kind of in the middle between writing something managed and unmanaged. So I thought, what if the managed runtime itself is managed? So to make these assumptions even further and make everything managed. So there will be literally no native C++ code inside the runtime. And I was wondering, has anyone tried to do such a crazy thing? Just to validate the craziness of the idea. And then I started investigations, as typically on the platform field and the runtimes field, a lot of interesting research is happening in the JVM area and around. So for example, there is a Graal AVM runtime, which is just something very similar to CoreRT in the end. So a lot of this runtime is written in Java. Even JIT is written in Java in it. So it seems that, okay, that idea was validated, and CoreRT direction is valid. But also I meet the JAX RVM, and JAX RVM is even going further. It is a JVM virtual machine written entirely in Java. Only some small C-based bootstrapping is happening inside. So because of that, we have some very small unmanaged part that stores everything, but everything else is written in Java, including JIT, for example, and the other parts. So it seems pretty encouraging, like, okay, if JVM is doing such thing, let's try to port the whole idea to the .NET ecosystem simply, to write something like JAX RVM in .NET. And as the homepage of this whole project says, JAX RVM was provided and was designed as a flexible open testbed for experiments to prototype various virtual machine technologies. And this goal has been achieved, so it is noticed as a useful vehicle for research. A lot of scientific papers and publications were around JAX RVM because it is so convenient to, in Java world, to have the runtime written in Java. It just opens and triggers and encourages, we can say, drives and just experiments on the field of the runtime itself if it is written in Java. So in the end, why the idea of the whole Mobius? It's a crazy idea of having Mobius. First of all, to make something very similar. So to have something that is for research and experiments. And it will be much easier and faster to prototype various parts if you have everything in C#. So you can, for example, write your own GC or just fine-tune some parts of the current GC or the current JIT. Obviously, for me personally, it is also for learning, so I have a possibility to learn a lot about the structure of the runtime and its internal dependencies, which then I can teach about, so it is a, let's say, dual benefit for everyone, and also for abusing, as I'm saying, or just learning C# and its newest low-level stuff. So such a code like the runtime written in C# sounds like a good piece and field for and playground for testing all these spans, stack allocs, unsafe class, and all the low-level stuff that we can have in C#. Even discovering some bugs that I am able to meet because I'm doing crazy stuff in the C# itself. For fun, obviously, this is all for fun also. The more problematic thing is whether it is for performance. And the very first, let's say, thought that you can have when you see that I was designing Mobius as a runtime running on another runtime, that it should be and it will probably be super, super slow. And I will just elaborate about it in a minute. So the whole idea of Mobius has been coined, and now just by saying a few sentences about about why, now let's move to the how part. So how it is designed, some design fundamentals of doing such crazy thing. So first of all, we can elaborate about two levels of runtimes now. First, we need our application, obviously, that we would like to compile and run. So it is any application in the world, any .NET applications that you would like to run. And then typically you run it on .NET Core, on .NET 5 runtime. But in my case, you will run it on Mobius runtime, which is managed. So this runtime will run on .NET Core. So we have this sandwich here, two levels of runtimes, including my own Mobius one. So it seems like pretty mind-blowing. We have two layers of everything, like two layers of JIT code, two runtimes, two GCs, and everything is doubled. How it may all work. So this is and whether it will be so slow that you can imagine that everything will be twice slower or even more times slower because of all that. Not necessarily, because if we need to understand what the runtime really does in terms of running your application. It is taking the IL code and it is JITting it into the native code. In the end, your application runs as a native application. It runs executing binary code of your machine. So obviously the JIT quality matters, how the good code is emitted by the JIT itself, but then it mostly runs as a native speed because it is just executing the native application code, the binary code. So in these terms, we can say that the Mobius JIT quality will be the most important one, whether the whole thing will run very fast or very slow, not the idea by default. So when you have something like that, you can imagine that, okay, I'm having my application, it is just compiled from C# to IL, and then when I running it, the Mobius as my runtime will JIT compile it, and it will be just running as a native code because my JIT has emitted the native code of your application. And 80% of the time, it will be just that. It will be just executing the native JITed code. And it will be not matter whether it was emitted by Mobius, .NET Core, or anything else. It is just a native JITed code to be executed. Obviously, sometimes this code needs to ask the runtime for something. The very typical thing is allocation. So if you are newing up something here in your app, then the JIT will emit the allocator code that will make a call to the runtime asking for the place for your object. So allocations will be one of the most typical ways how the JITed code of your application will call back my runtime, my Mobius. And then obviously, because my runtime code is managed in C#, it will be also JITed, but now it will be JITed by .NET Core. So the allocator code will be JITed and will be now executed as a native code just because it has been JITed by .NET Core or 5. So yes, we have two levels of JITs, but I would say 90 or 80% of the application will be just here executing the native code with some occasional, not so frequent calls to the Mobius code, which then will have even less frequent calls to the regular .NET Core code of the runtime. So it makes sense, like it for sure not be so fast as the regular .NET application running on the regular .NET Core, but the difference doesn't have to be so big that it will not make any sense to run anything or that. And also remember, it is all for experiments and research. So in the end, the performance maybe is not so important here, but still it may be valid to run something on it, not to just wait as it will be not 10 times slower, for example, than a regular application running on the regular runtime. So we have these two levels, and conceptually, all that matters is the JIT that will produce some code that will be run as your application. And then some fundamental questions. For example, if I have two runtimes, what I will share between them, like JAX RVM is sharing something, the Java is running on itself. And in case of Mobius, I could also think about sharing some information, like, for example, I could reuse the whole type system at runtime from the .NET Core, or I can think about sharing some memory and share some GC maintenance of the memory between those runtimes. But it would introduce some limitations, and I was really thinking about introducing and enforcing, encouraging experiments, so I didn't want to have any constraints. So the obvious choice was just not to share nothing, and to have the totally new thing that you will be able to implement. So there is totally nothing to be shared between the Mobius and the .NET Core. Everything needs to be written from scratch, which is nice. And because now you can write anything that you can imagine, and moreover, by replacing things. So everything should be defined in a way that you can easily replace the JIT, or you can replace the GC, and it will still run with your own implementations. So if the Mobius runtime is written in an inefficient way, like not so allocating way of doing things, typically it will be pretty rarely calling the .NET Core, because it will be it will not need to call it. So it sounds like a valid idea still. and while still having own implementations of everything. So literally there was a point in time when I was just clicking file, new solution, and creating a new solution for the whole idea. And I needed to think about the structure. So obviously there is a host, which would be a console application, taking your DLL and executing it, asking the runtime to execute it. There will be some core part of the library of the whole idea that will contain, let's say, the putting all the pieces together, the type system inside, then the GC and the JIT as the two most important blocks that I would like to treat as plugins. So no constraints, no any assumptions about the GC and the JIT, so you can replace it with your own implementation, which obviously makes a really big trouble from the perspective of the API design, because the runtime really relies typically on some assumptions between the GC, the JIT, and other stuff. So it is not so trivial to make an API that will make all those things plug-enable, but still it is one of the main research areas here, one of the most important thing that I need to find out how to do that, and some auxiliary projects for helpers and other stuff. So having all this, I must say, maybe you have seen my talk last year, or maybe you have just heard about the idea that you can replace the GC in the current .NET Core. So there is this local GC initiative, and I started to implement my own custom GC. And I started to do that, but I postponed this project a little because I've met a lot of important limitations between the GC and the runtime. So the API introduced there is pretty limited, which forced me to stop the work, because that was not something that was encouraging a lot to make the further development. So here, the totally different thing I would like to see. API is so flexible that you can change anything and you write any algorithm you want. Some design fundamental choices, like whether the code should be async or not, the decision was pretty simple. It should be not async, because the runtime itself is not async. It is no IO bound so much. It is typically just the JIT, which is just CPU bound code. And then important decision, what about the JIT, that I will cover in a moment. Unfortunately, when writing your own runtime, there is this pretty blocking, pretty boring part that you need to overcome, the type system. Metadata type system, the whole thing, which takes a lot of space in the ECMA standard, needs to be your friend, and you need to read all of that and need to implement it. It's not rocket science, it is like operational bits and bytes, but you need to support the type system, obviously, to make execution of your application. The GC itself is super interesting, so obviously I like this topic. It is my beloved topic. And then a lot of decisions, how the GC should be implemented. But this is a second level decision, because in Mobius, everything is a plugin, so the GC is also a plugin, so it doesn't matter a lot how the current GC is implemented and what it has as a functionality. It is just the API between the runtime and the GC important, not the GC itself. So this decision how the GC should be implemented is a little bit postponed by me. But there is a second thing to think, which is super important: object memory layout. This is something not trivial, because every runtime in the world assume there is kind of some object memory layout. .NET Core expects some object memory layout. Mono expects some. So we have there, for example, information how is stored the identifier of the type, whether there are some reference counters before and after, or maybe not, what are the representation of references, and so on and so on. So object memory layout is pretty important thing that other pieces are heavily relying on. So this is another thing that I should really make it plug enable, and this is a lot of this is pretty let's say the hardest thing that I'm currently thinking of, how to make it plug enable and customizable for experiments. Okay, but even before that, we need something that will execute our application. So we need kind of JIT. And now we need a decision whether it should be in just a regular JIT, or maybe we can just use an interpreter. Interpreter is a simple idea in the end. It is just a huge while with a huge switch inside, which will just read your memory byte by byte, opcode by opcode, and will just react to the particular opcodes. Something that was described 2 days ago when there was a talk about the Game Boy emulator. We just read a memory from some place and then interpret, okay, this is this particular instruction, so just let's execute this particular method that will handle it. So this is a pretty easy concept. We just interpret byte by byte, opcode by opcode, the whole program, which sounds like a slow thing, and it is in the end slow thing. It is just a huge switch inside the loop. So there are some advantages still, like it is super easy to implement. You are just implementing opcode by opcode, the reaction to every opcode. And then bigger even advantage, it requires no executable memory region. You can just take a memory, read from it, and you are just doing some actions based on it. You don't need to emit any native code. So .NET Anywhere was using it, for example, as one of the modes, and there are some platforms that does not allow you to emit executable memory regions, like Apple operating system on iOS doesn't allow you to do that. So you need to interpret something if you'd like to execute there. So interpreters have their own use cases, but they also disadvantages, like first of all, it is super slow. It is just a loop with a huge with a huge switch inside. So the branch predictor on the CPU is just screaming because it doesn't allow you to optimize anything. And also, it is not so fancy for learning how the JIT should be implemented. It is just interpreter. We are just writing this interpreter, and that's all. So nothing super interesting. So there are some examples. Mono has interpreter mode, and this is one of the reasons why Mono is used in the Blazor WebAssembly, because WebAssembly currently also is in sandboxes mode. It doesn't allow you to emit the code to be executed, so it needs to run in an interpreter mode, and Mono has much better interpreter than the very experimental one in .NET Core, so the Mono has been chosen here. And .NET Anywhere was interpreter based also. But okay, so if not interpreter, let's write the real JIT. And it has obvious advantages, like it may be super fast. The sky is the limit how you will optimize the code that is emitted by the JIT. And obviously it allows you to learn how to write a real JIT. But the problem is you need to, the sky is the limit in terms of implementation. So it may take a lot of time to write a really good JIT. It is like for a lot of people for a lot of years probably to write something that will be sophisticated enough to be production ready. And yes, and it has this disadvantage. It requires executable memory region because we emit some instructions that then will be executed as a regular application. And almost every .NET runtime is using this approach. So it sounds like I should follow this direction, but there is something in the middle, and there is something more, which is called threaded code. You can look at the Wikipedia at it. Threaded code is a concept, a programming technique where the code has a form of consists of subroutine calls. So instead of making very sophisticated code, our threaded code is just a long list of subroutine calls. And those subroutine calls may be reactions to our opcode. So in this threaded code mode, we are doing something like JIT, because JIT is in the end, we are emitting some code, so there will be no interpretation phase. And the JIT in this mode will just emit a long list of calls for every CAL instruction. And what's even more nice here, it may directly implement the CLI stack-based machine, because if you look at how the underneath the CAL code looks like, it is operating on so-called evaluation stack. So just not having a lot of words about it, just let's show you an example. Imagine that you have a code in C# that adds two numbers. And in case of C#, you will write obviously A plus B, and that's all. Then it will be compiled to the IL code that looks like that. And because it is stack based, it is just translated to an operation on this virtual evaluation stack, saying that, okay, so let's push a number A on the stack, let's push the number B on the stack, and then the instruction add is taking the two numbers from the top of the stack, adding them and replacing the result of this addition to and putting the result of this addition on the stack. So in the end, we replace the numbers A and B from the top of the stack by the result of the addition. This is how the whole your application is looking from the IL perspective. And this now can be emitted to a super sophisticated JIT code using, for example, registers and so on and so on. But in case of the threaded JIT, it may be JITted to something as easy as here, like in the pseudo assembly code. We are just converting every instruction in the IL code to a call to a subroutine doing what should be done. So, for example, if we have a call to a subroutine responsible for pushing something on the stack, and this is an evaluation stack in the IL terminology, but we now using the real stack for this evaluation stack. So we are just putting this number on the stack. Then we are putting the second number on the stack, and the call to the add instruction will be just taking those two numbers, adding them, and putting the result on the stack. So we can have this pretty nice one-to-one mapping between every IL instruction, and we can emit some real native code that will execute this. This is beneficial because it is now just a regular native code that will be executed by the CPU without no interpretation. So it is something exactly in the middle, a perfect middle ground. It has a tolerable difficulty because it is good for start. I am able to map the one-to-one every IL instruction to some subroutines. So the logic looks like almost like the normal interpreter, but in the end it is emitting a native code. Okay, it will consist of a lot of calls, but calls are extremely optimized nowadays, so it is not so super slow as we may expect. And moreover, it requires the executable memory region still, so it behaves like a normal JIT. It has the same limitations, so it is a perfect ground for learning also. So, okay, so this is the fundamental decision. The current JIT implementation in the Mobius is a threaded one. Obviously, it needs to be written in a pluginable way, so in the future you may change something, you may replace it totally, or you can fine-tune something in the current implementation. So those were the design decisions. How all this is working on the code level. Just a few examples, because it would be pretty boring to cover everything. So just a few examples. The metadata, I'm just reading with the help of the PENet library, nothing super sophisticated. So there is a pretty nice library that is just able for reading, for example, Windows portable executable headers. And from there, I can read addresses where the metadata are, to the point when I'm able to find every method address and its size in terms of IL code, obviously. So PENet helps me here just to find the method with the given, for example, the entry point of our assembly, and just read it from the memory. So nothing super sophisticated. the more interesting part is the JIT implementation. So I'm allocating pages that will be used to populate the code that is emitted by the JIT. And what's important, I'm using this execute rights, so I will be then able to call methods from there. They will be able to execute because they have this execute rights. And obviously I need also to have the rights because I will emit the code there. And then I had only to write the JIT emit method, like, okay, so assuming that I have an address of the method body in terms of the IL code, and the region when it should be emitted, let's just implement the JIT. The simple thing just to do that at this stage of the development. And when I will just JIT emit it, I know that under this pointer, under this address, I have a method that can be executed. So I need some magic in C# that will be able to call now from the managed code, the unmanaged method that just has been emitted under the given address. This is all supported in C#, what is luckily for me. So for example, if you have an address in a memory and you would like to call it, it sounds like a super low level stuff, and in the end it is. There is IL instruction for that. It is called callee, and it is just the instruction that is just taking an address, and it is just assuming you are really know what you are doing, and will start to execute a code under the given address. So if I would like to do something like that, I can, and this is an example in the IL, you have a, let's say, managed method. You are just taking an address of it and using this instruction to call it. All this is for managed code, and all this is also recently exposed in C#9 as the function pointers. So if you have met this, that the C#9 introduces function pointers, it is nothing else like exposing those two instructions, the callee and the ldftn, which takes an address of a method, and it is now exposed to C#. So delegates will start now to have stars as an address of a method that may be taken with this operator. That's nice, and it's nice that it is exposed to C#, but unfortunately, I cannot use this approach because, as you see, the pointer to the method needs to be strongly typed. So and this is fortunate, obviously, for the perspective of the regular code, because I know that I have a pointer to a method that accepts an integer and returns an integer as a result. This is a type safety on the C# level, which is super nice. But imagine and remember, I'm JITting a code from the external application, and I totally have no idea at this point what are the return types and arguments of this method. It comes from the external code, from the application that you are running. So I don't know at the compilation level what are the types, what is the signature of it. Because of that, I need to make some IL emitting on the level of the runtime that will call and use this callee instruction directly. I'm not showing this not to scare you enough, but it is working. So in the end, I'm able to take an address of every method and call it with the help of the IL emit functionality in the C# and standard libraries. So this looks like that. Having a method pointer, so imagine that I'm saying this, okay, I have a method that I would like to call, and this method is under this given address. I'm using the dynamic method and its possibility to emit IL code. Maybe you have seen this before, maybe not. We have such low-level things in .NET. So you can just in time, by the use of the reflection, emit your own methods dynamically, and I'm just doing that here. I'm just using it to emit the calling instruction to call a function under the given address. Still with that strongly typed signatures, so this method is a first iteration. The second one, which looks much more scarier, is using the dynamically created signatures, but I will not show you that, not to scare you totally. So, but believe me, I'm able to IL emit a code that will call a given method with a dynamic signature. So we have all these pieces in place almost, because obviously this is what the JIT will be doing. But JIT, as the name states, is the just-in-time compiler. So it does not compile everything in advance. It is just-in-time compiler. So it is not that we are given an assembly and then we are compiling everything to native code, because we don't know what will be called in the end. So just-in-time means we are only calling in a lazy manner. So only if someone calls a given method, only then JIT kicks in, JIT make the JIT compilation, and now we start to execute the JITed code, the native one. So JIT is lazy, and I need to make this laziness feature into the Mobius, obviously, because it needs to be JIT, it needs to be just in time. So similarly to the approach of the real runtimes, instead of when I have a method, the managed one, I'm putting some kind of stop that is just for the starting and for initialization of the JITing of a method. So in the end, every method address in your application, if you have an assembly and you have a method inside a type, including the main method of the given program static class, all those methods points to some JIT stub, and this JIT stub is there only waiting to be called. And if you will call it, it will start JITing the method under the given address and replace the result, and then we'll execute it. So in the end, we will have the method address pointing to the JITed code. So the JIT stub will be replaced with the JITed code. This is how it is working in every .NET runtime, including the Mobius runtime. So exactly the same approach has been taken by me in Mobius. And this probably is not a moving piece, so it should be like that in the core part of the Mobius, so it shouldn't be plug-inable, because it is on so level part that I will be really afraid of even allowing replacing that. So we will have nothing fixed in our structure of the code. So in the end, if you have our application, the unmanaged code that you are executing, the part, for example, you are just JITing the main method, and at some point in time, you are executing another method, it will hit this stub, and this stub will hit the call to the JIT method. And this is the one that will be responsible for JITing the whole method and executing it. So some handle magic to take just metadata of the given method, and then we are accessing the IL body of the method, and we are in place. So we are inside the runtime. In the managed code, as we see in the C# code, we are just having the IL body as a span of bytes to be interpreted. And the only thing we need now is to emit the assembly, the native code for this, based on the IL of the method. For doing that, I'm using the super nice ICE library, which is a high-performance instruction decoder, disassembler, and assembler that can be used from C#. So with the help of it, it exposes a special type of writer that allows you to use those kind of methods. So if you have ever written something in the assembly, that's exactly that. Every assembly instruction is there exposed as a method. So you are writing your code like assembly, but from C#. And these all instructions are just building your assembly, and then you are writing it and assembling it as a binary code that can be later on executed. So with the help of this ICE library, I'm able to emit a native code from C# to a given memory region, and then later on it can be executed as a method. For example, here, super simple method that is just having some prologue and epilogue, which are not so important, and it is setting the result of a method to 44, because the RAX register is the register when we expect a result of a method. So it is a hard-coded method that always returns 44. Pretty nice that it is all working. And then only one more thing to have in place to make all those pieces working together. We need to have possibility to call back the Mobius itself, like the allocator. If I'm hitting the IL instruction called new object, which means the code wants to have a new object, then I need to emit code that will call allocator. And an allocator is a code from Mobius. So it is the reverse call from the unmanaged code to the managed code, which is my Mobius code. From the perspective of the code, it is a magic. Like, I'm showing this because I'm really super happy that the .NET runtime and all this infrastructure is supporting it out of the box. So imagine that I have a pointer, and this pointer is just an address of something that is responsible for calling my allocator, which is a code in C#. So if you have ever written something in assembly, it is as easy as using the call instruction with the proper address here stored in the RAX register. So this is something that from your native code will now start to execute the managed code. And how it is happening? Because it looks like a magic. Imagine you have a totally native application, you are executing a JIT code, native one, and now all of a sudden it starts to call an address which should come back to the managed code, which should be JITed. And this is all because the reverse painvoke magic inside the CLR. So if I convert an address of a managed code with the help of this special instruction, which is called get function pointer for delegate, it will wrap everything around and connect all the pieces. So in the end, you have a pointer that will be responsible for the whole marshalling. So now you can do exactly what I said. You have a method inside an instance of the GC class, for example, the instance method allocate. And if you will provide an address of it to this get function pointer for delegate, and then you have a pointer, and then you will use the call instruction on this pointer, out of the sudden, you come back to the native code, and you will start to execute, you will come back to managed code, and you will be starting to execute this particular method. You can even set breakpoints here and so on, because you really start to execute this code, which is in C#. If you are aware of some details here, you can wonder about what about the instance, because here I have just a pointer that I'm calling, and when the runtime knows that it is this particular instance, it knows because this function is responsible for some magic marshalling that stores the pointer to this instance. So mind-blowing things happening here that allows us to make the call from the runtime to the managed code and back. So in the end, a lot of such very interesting stuff that you totally will not use in your everyday life probably, but if you are interested in internals, they are mind-blowing and really nice to have knowledge of, which I hope will be useful for all those experiments and research that I described previously. So now the question, because it is slowly good time to end, when all this will happen, that you will, for example, be able to play around with it. So obviously the amount of code needed to be written when you would like to implement your own .NET runtime is around infinity. So a single guy as me is not able to write your own .NET runtime. Even .NET Anywhere by Chris was limited. As far as I remember, it doesn't support generics and other stuff. but it is possible to write some vertical proof of concept, so something that is having all the pieces all together working and giving some super slow piece of functionality that will allow to execute, for example, Hello World application. So I'm slowly getting there, the vertical proof of concept with some JIT, with some GC, zero GC because it is something that will only allocate, but well, it is a plugin, so you can always write your own GC, and without threading support, which I'm be afraid of adding at this point because it adds another level of complexity. So it will be single threaded. And all this should happen on GitHub because currently Mobius is private repository, which is really a pain for me because it is not so super secret code that I really like to keep on my own, but it needs some refactoring, let's say, before making it public. So I'm waiting for this because obviously this is a super low priority pet project, so I don't have so many time for it. So this time when I will open source slowly comes, I hope it will come very soon. For sure this year, having without any general promises, for sure this year should be the one when I will open source it with some functionalities, and then I hope some people will get interested, maybe they will contribute. So just closing up, have you ever wondered how the .NET runtime works? If you were, now you will have a pretty C# based runtime at hand, so you will be able to analyze everything, debug everything, and I haven't even mentioned that, but you know, debugging the full .NET runtime is pain because it is C++ code and it is not so convenient sometimes to do that. Imagine that you have the whole IDE support for debugging. You can use debuggers from Visual Studio or the fancy stuff, all the diagnostics to analyze the .NET runtime written in C#. This is super nice for learning and also super nice for contributing. So if you have a C# based runtime at hand, you can easily add something, you can easily experiment, try to modify something, analyze the results, contribute. Obviously, no one will use it, at least on production, so you will be not afraid of destroying anyone's business because it is only for research and experiments. So I have a fingers crossed all the time to make it working and publicly available on GitHub. And having said all that, this is all. There is a single link when I'm describing almost the same things as I described today, so nothing super more advanced there. And this still private repository that eventually should be opened. I really hope sooner or later, even if it will be not complete, for sure it will be not complete. So done is better than perfect. I will open source something, at least for you soon. And that's all. Thank you. Thank you for staying with this crazy idea of low-level stuff and all these assembly-based slides, which are not so common on .NET Conference. And if you have any questions, I don't know if we have any time for questions. I will be still on track number 5 on Slack, so maybe then we can move with any discussions or questions that you have.